Hello everyone. In this video we're going to learn about two important types of logarithms known as common and natural logarithms. We have previously learned that logarithms are well defined for any base b as long as b is a real number, it's positive, and it's not 1. But two particular values of b are utilized most often in mathematics and the sciences. One is base 10, which of course we're all familiar with, the number 10. The other is base e logarithms, which may not be that familiar to you. E is a number which is irrational and it's a constant like pi. Its value does not change, and it's approximately 2.71828. So as you know, irrational numbers have a decimal form which never ends or repeats. Therefore, this is just an approximation rounded to 5 decimal places. And the actual source of E, where it comes from, is going to have to wait till we get to calculus, because it requires the understanding of an infinite series that is depicted down here. E is named after the famous Swiss mathematician Leonhard Euler, who obtained many extremely important results using the number E. In fact, base E is so important that when you go into more advanced mathematics classes, you're hardly ever going to deal with any other base than E. Or what I really mean is any base other than E. Base 10 logarithms are called common logarithms because they are utilized quite often in the natural sciences. And the notational convention is that since they're used so often, we just drop the 10. And when you see log x and you don't see a base, you can automatically assume that the base is 10. Of course, a logarithmic expression without a base doesn't make any sense. So when you see that, you know that the base is just invisibly there, it's 10. Just like, for example, with radicals, square roots are so often, we just don't write the 2 in the inside the location of the index, and we know that automatically it's a 2. So in the same way, so the pronunciation, of course, is just log x. Base E logarithms are called natural logarithms because they do occur in many natural processes and events. The convention for notation here is when we are dealing with the natural logarithm, we summarize all of that into just ln x. And it's pronounced exactly that way. You just say ln x. Some people like the longer version and they say natural log of x, the same thing. And a few people actually call it ln x for some reason. They prefer that. I personally prefer ln x to all of them. So when you see ln x, you have to automatically in your mind imagine that it's just a logarithm. It just happens to be log with that new base e we just learned about, which is somewhere between 2 and 3, closer to 3, 2.7 or so. So that's exactly what you're looking at. You're just looking at a log base e logarithm. All right, so let's go ahead and do a few examples to get comfortable with these two kinds of logarithms. Here, of course, since we see the log but no base, we automatically know this is log base 10. So we want to compute it and then explain what it actually means. So basically, we just go ahead and write it in this way, and if we calculate it on just a regular scientific calculator, because as you know, the power of 10 that gives you 20 is not going to be a nice simple power, so we'll need a calculator for that. All right, so here we will just go ahead and push the log button and go ahead and type 20 and hit enter. So we get approximately 1.0 let's go to 4 places, 3010. So we get from the calculator that this is approximately 1.3010. So here we want to know the significance of what that means. Remember, for that we'll go to full notation. So we realize we have just computed log base 10 of 20, and we have found it to be approximately 1.3010. Now, we know the relationship between logarithmic equations and exponential ones. We know that log base b of x equals y is the same thing as saying b to the y equals x. So if we use that here, we're going to get 10 to the power of 1.3010 is approximately 20. So when we compute log 20, we're basically finding the exponent that needs to 10 needs to be raised to the power of in order to get 20. We can verify that quickly by going ahead and typing 10, that's 11, so let's go to 10 to the power of 1.3010, and when we hit enter, we should get a number not exactly 20, because remember we did some rounding, but it should be close, very close. And as you can see, that is extremely close to 20. Of course, the more digits we would use, the more accurate our answer would be. And of course, if we go to the extreme of just raising 10 to the power of log of 20 itself, then we would get exactly 20. Well, notice it's gotten closer. This is the limitation of calculators. So even in that form, of course, notice it's much closer to 20. But the calculator itself, even with log 20, even if we don't limit it, it itself has a limitation. So it's just going to get extremely close to it. But some calculators actually end up giving you 20. It depends on the calculator you're using. In fact, I believe if we take a look at the TI and type in 10 to the power of log 20, it does indeed give us 20, as it should. So it depends on the calculator you're using. Some will give you the exact number and some don't. Of course, we realize this is an exact number. So when we write 10 to the power of log of 20, we know log of 20 it is precisely the power that you need to raise 10 to the power of in order to get 20. So we have that exact statement. But if we're going to approximate, then we're going to use this double tilde notation. Here we have log of 10,000, log base 10 of 10,000. Even when the base is not written, I often like to write it because it will help me understand it better, because I realize I can do this without a calculator. Because what am I looking for? Remember, when you want to find the log, look at this invisible exponent right between these two numbers, so that when you raise the base to the power of that exponent, you get this number. And of course, you know 10 to what power gives 10,000. That's an easy answer, and we know that that's going to be 4. So with some of these, you will not and you should not use a calculator. All right, here we're computing the natural logarithm of 20, or the ln of 20. And of course, you know, log base e is an irrational number to begin with, so we definitely will utilize the help of a calculator for this. So we'll go ahead and type in ln of, not second, let's try that again, ln of 20, and that's the number we get approximately. So if we go to 4 places again, that's approximately 2.9957. So we have ln of 20 is approximately 2.9957. Let's make sure that was the case. Now, we also want to know the significance of what we have just found, because, you know, we can teach a child to type in ln of 20, but the child won't ever understand what it means. But we have the capability to know what that is, so we always should. So basically, remember, we have just computed log base e of 20, and we have found that to be 2.9957. So we know that if we convert that into exponential form, we get e to the power of 2.9957 is going to be approximately 20. So when we calculate ln of 20, we're trying to find the exponent we need to raise e to the power of in order to get 20. Now again, we can verify that if we just go ahead and type in this time e. That's the second function of ln. Usually you have to push either second or shift, whatever it is on your calculator, and you end up with typing in the exponent 2.9957. So the moment of truth, we should get something extremely close to 20, and of course, once again, we do. So let's see if it makes the same error on, it's not really an error that it made when it came to the previous problem where we did 10 to the power of log of 20. It's just that it went completely by approximational method, approximating methods. It didn't have any exact algebra built into it. Obviously, the TI does. So here, if we go ahead and type in e, okay, let's cooperate this time. Let's see. So if we type in shift e to the power of ln of 20, let's see if it's still gonna do that. Yeah, so it's doing this by approximation again. That's why it didn't actually give us 20, but as you can see, that's virtually indistinguishable from 20. So here we have ln of 10,000. So we're going to go ahead and utilize the calculator in our first phase, and we will just type in ln of 10,000, and there's our answer. So 9.2103. And as far as understanding it, remember, we have just computed log base e of 10,000 because that's exactly what ln of 10,000 is. And we have found it to be approximately 9.2103. Converting it to exponential form tells us that e to the power of 9.2103 should be approximately 10,000. So if we test it out, we can just type in e to the power of 9.2103, and once we hit enter, we expect to get something very close to 10,000. All right, so Again, the more digits we use, the closer it will get to 10,000. Okay, here we have a couple of problems that you should not need a calculator for. I encourage you to try them on your own before you come back to the video. All right, so for the one on the left, we know that we have log base 10 of 10 to the 5 that we're trying to compute. And of course, if you remember, log base b of b to the x is always just going to be x. B to what power is b to the x? Of course, the answer is x. So here we know we're just going to get 5. On this one on the right, we know that ln of e to the 5 is just another way of saying log base e of e to the 5. And of course, again, because the base of the logarithm and the base of the power that we're computing is the same, we have the same scenario, so we know we're just going to get the exponent. So here we're just going to get 5. These are very simple but extremely important concepts that you'll be encountering quite a bit, so make sure you get really comfortable with them. Here's a couple more which will not need a calculator by any means. We can't use it anyway because there are variables involved. So here on the left we have log base 10 of 10 to the power of 2x plus 3. We know that whenever these two bases are the same, we're just going to get the exponent, so we get 2x plus 3, and that's where we leave it. On the right side, of course, the exact same thing happens because we have log base e of e to the 2x plus 3. So once again, we're just going to get 2x plus 3. All right. Now we'll go ahead and take a look at some applications of these two very popular types of logarithms. So let's go ahead and start with looking at the pH. You've probably heard the name, the pH of a basically water-based solution. As we know, this is going to be a common log application. And what the pH does in chemistry, it's called the power of hydrogen. It's a scale that we use to specify how acidic or basic, also known as alkaline, a water-based solution is. Now, here I've made a chart for you that explains the categories that pH will make a body of water fall into. If the pH of a body of water is between 0 and 7, that is considered acidic. It's actually that body of that type of water will be known as an acid. If the pH is exactly 7, that's where pure water comes in. And if the pH is between 7 and 14, we call it alkaline or basic. Now, of course, this table covers most types of water-based solutions that you will see. Extremely acidic solutions can have a pH of that is less than 0, and extremely alkaline solutions can have a pH greater than 14. But both of those are extremely rare. So we calculate pH using this logarithmic equation. We have pH equals negative log of this complicated looking thing. It's basically just H3O, and then we have a plus up there. This here is called the hydronium ion concentration. The units we use for that is moles per liter. You can probably consult your chemistry book or your chemistry teacher for more information on that. I can just tell you that 1 mole of a substance is not 1 molecule. It's a whole lot of molecules of that substance. It's the, as you know, the Avogadro number of many molecules. So, and usually it's common practice that we round pH values to the nearest tenth. So let's go ahead and take a look at an actual problem involving pH now that we understand what it is and what it signifies. Okay, so you're driving down the road and you're passing this beautiful lake, and you see a sign that proudly proclaims that the hydronium ion concentration of the lake water is 3.15 times 10 to the negative 8. So what we want to do is find the pH of this lake water and see why the residents are so proud of that hydronium ion concentration that they've listed. So remember that here is the formula that we're going to be using. So we have pH equals negative log of H3O plus. I always write the original formula first before I substitute anything. For one, it minimizes the chances of making errors. And the second thing is, what happens when you write something 5-6 times over? You'll have it memorized with no problem. So this formula does not need memorization. If you need it, it will be given to you. The important thing is how to utilize it. Now, notice we have two quantities that could be unknowns here. One is the pH, the other one is this hydronium ion concentration. So all of that is just one number that we refer to. So one will be given, the other will not, and will be asked to calculate the one that is not given. In this case, the hydronium ion concentration is given, it's right there, and we want to find the pH. So we're just going to substitute this number where we see this H3O plus. So we get pH equals negative log of that number, 3.15 times 10 to the negative 8. Now we go ahead and utilize a calculator to go ahead and compute that. So let's clean this up a little bit. All right, so we have negative log, don't forget the negative, and then 3.15. If your calculator has one of these engineering buttons or scientific notation buttons, you can use it. In case it doesn't, I'll just show you that you can just type it as you see it. You can go times 10 to the power of negative 8. Then you go ahead and hit enter, and there you have the pH. Again, remember we usually round pH to the nearest tenth. All right, so we get approximately 7.5. So now we can see why they were so proud of it, right? Because that's pure water itself is 7, so this is even more alkaline than pure water. So well, pure water is not alkaline, it's actually neutral, but we mean it's very, very close to the pH of a pure water. So it's very, very high quality water in the lake. That's why they're so proud of it. And if you come back to the calculator, I just want to quickly show you the other notation that we can use. So if we just type in negative log, and we're going to type in 3.15. This time I'm going to show you how to use this button. It's the scientific notation button. So when you hit that button, you're basically not going to need to multiply, to write the multiplication, the 10, and all you have to type is the exponent. So right now we're just going to type negative 8. So as soon as you type, the system is ready to receive the exponent. It's going to put in the times and the 10 for you. So so it just will ask you for that exponent, and then you'll go ahead and hit enter, and of course you get exactly the same thing. So learning how to use that is quite useful. All right, in this one, notice what it did is it took this and turned it into its standard form rather than its scientific notation form. But the outcome was the same. All right, here's another pH example. Now, you've probably seen these popular bottles of what they call alkaline water, because they boast a pH level of more than 9.5. Remember, pure water is just 7. So this is supposed to be somehow better for your health. So a lot of companies like to sell these bottles of water now. So notice that they claim that their pH of their water is, when they put 9.5 plus, that means greater than or equal to 9.5. So if we just assume that it's 9.5, let's go ahead and calculate the hydronium ion concentration of this particular popular brand of water. So here's the formula. We're going to go ahead and start with the formula. So we have pH equals negative log of H3O plus. Now that's a lot of writing. So since it's the unknown, let's do something. Let's go ahead and let that H3O plus, let's just call it X, because that's what we're solving for anyway, right? So the equation becomes much nicer looking. So we just get pH equals negative log of X. All right, now notice that here we have the pH, it's 9.5. So we have 9.5 equals negative log of X. And if I get the log by itself, then we'll be able to go to exponential form. And of course, it's almost by itself. We need to get rid of this negative. So we're going to multiply both sides by -1. Like that. And so we end up with log X equals negative 9.5. Now at this point, I would like to bring in the invisible 10, which we know is there. When we see a logarithmic expression, we always know there's a base, even if it's not written, such as in the case of log or ln. So here we'll write it in just so that it makes it easier for us to transform this into its exponential equivalent. So again, let's remember that log base b of x equals y if and only if x equals b to the y. So when we go ahead and translate that into exponential form, we get x equals 10 to the power of negative 9.5. So now we're going to go ahead and get a answer for our hydronium ion concentration, which, as you recall, is exactly what we called the X. So we'll go ahead and utilize the help of a calculator. So we're going to go ahead and type in 10 to the power of negative 9.5. Now we hit enter, and there we have it. So here we can go to 4 places, for instance. So 3.16. We can even usually round those to 2 decimal places. That's good enough. So just deal with the problem according to instructions given if you're on a test or on homework. So 3.16 times 10 to the power of negative 10. All right, so that's how you calculate hydronium ion concentration if you know the pH. In the last problem, we were given the hydronium ion concentration, asked for the pH. In this problem, we were given the pH and asked for the hydronium ion concentration. Okay, another handy application of common logarithms is the decibel level. You may have heard of it. A decibel is a unit measured, used to measure the loudness of sound. And in order to be able to compute it, we need the intensity of a very faint bass sound, which we choose. We call it the threshold sound. So we compute the intensity of a very faint sound, and then we also need to provide the intensity of the sound, which can be measured with various devices, of the particular sound that we want to compute the loudness of, and using this logarithmic equation for the decibel level, the units are lowercase d, uppercase b. Those audiophiles among you, I'm sure, have seen that measurement unit. And basically, as far as decibel levels are concerned, when we do the computation, any decibel level that's less than 85 is considered safe. Decibel levels greater than or equal to 85 but less than 150, meaning decibel levels between 85 and 150 left inclusive, are considered unsafe. And when you go above 150, you're going to be in the extremely dangerous zone. Here, to be really technically sound, we should have greater than or equal to. All right, so that's when you could experience possibly permanent hearing loss. And you definitely want to avoid that any kind of loud sound, because the ears, they seem tough, but they're much more sensitive than they appear. All right, so in this example, a friend of yours who is a science enthusiast uses a fancy gadget to measure the intensity of the sound coming out of your latest state-of-the-art headphones, and they calculated to be this much about that threshold sound which we discussed. And we want to know if you're adhering to safe listening practices or whether you should go ahead and turn down the volume. So just to remind you, let's take a look at that formula again. It's a simple formula: D equals 10 times the log of that quotient. So we go ahead and write the formula down. D equals 10 times the log of I over I0. Notice that the intensity is always given as some number times that threshold intensity. So here we're just going to substitute. So we get 10 log of, we know that the intensity of the sound coming out of your headphones is 3.215 times 10 to the 9 times I0 divided by I0. Notice this always happens because we always give the actual intensity of the particular sound as a multiple of the threshold intensity, and we have the threshold intensity in the denominator too. These are always going to cancel out. So like so. So we end up with just equals 10 times log of 3.215 times 10 to the 9. So for that, of course, we'll go ahead and utilize a calculator. So we get 10. Oh, let's clear that first real quickly. All right, so we get 10 times log. Make sure you use the log, not the ln. So log of 3.215, and we'll go ahead and utilize this button times 10 to the 9, and we go ahead and hit enter. So the decibel level of the sound coming out of your headphones, if we just go ahead and give it to the nearest whole number, is around 95. All right, so let's go ahead and compare that to our results here. So you see, you are in the unsafe zone. I mean, is it really bad? Well, no, you're pretty close to the acceptable zone, but it's probably safer to go ahead and turn it down at least a little bit, okay? Of course, we always want to present our answer with the proper units, and here the units are decibels. We use a lowercase d and an uppercase b, as I mentioned on the previous screen. And there you have the decibel level coming out of your headphones. All right, as a last example, let's go ahead and take a look at an atmospheric pressure problem. This is a natural log application. All right, this fancy formula here gives us the altitude measured in meters that corresponds to a given atmospheric pressure of P millibars. Now, what we want to go ahead and calculate is the altitude that would correspond to an atmospheric pressure of 500 millibars. So with this kind of a problem, it looks fancy, it sounds fancy, but it's extremely simple. All you have to do is know what each letter represents. A of P is altitude at pressure P. This is not multiplication, this is functional notation. You're presenting altitude as a function of the pressure. So P itself is the pressure. So since here we're given the pressure, we have this, we're looking for this. So really what we're computing is A of 500. So we're going to get 51,600 minus 7457 or 7,457 ln of, now we're going to replace P with 500. So now it's just a matter of carefully entering that in one shot. So we get, we lost our window. Okay, we have it back. So we get 51600 minus 7457. This time we're going to hit the ln button, not the log, ln of 500. And then we'll hit enter. And we can see the result is 5257.67. 5257 point, so approximately 5257.67, and of course the final answer should have the proper units. We know we were calculating altitude, so that will be in meters. So here we have become familiar with two very popular types of logarithms: base 10 logarithms, also known as common logarithms, and base E logarithms, also known as natural logarithms. So make sure you practice and be safe until our next video.